The Andromeda Galaxy is known as the galaxy that brought to light the fact that the universe and creation itself didn't revolve around us. It was proof that the Milky Way isn't the only galaxy on Earth, and that we might just be a speck in the greater universe. Over the past century, we've actually learned a lot about Andromeda, but most of the information has been from Earth. Now that we have access to instruments like the James Webb Space Telescope, things are a lot different. It turns out the Andromeda Galaxy is not what we thought it was. Data from the James Webb Telescope has shocked the entire industry. Join us as we bring you all the details on the truth about the Andromeda Galaxy and the shocking truth about it that we didn't see coming for an entire century. A century ago, the Milky Way was commonly thought of as a band of faint, wispy, white lights stretching across the night sky. This perception was influenced by the limited technology of the time, which prevented astronomers from discerning individual stars within the Milky Way. People held various beliefs about the Milky Way, often associating it with the center of all creation. Italian astronomer Galileo Galilei revolutionized our understanding of the Milky Way in the early 17th century. Using his newly developed telescope, he made groundbreaking observations that challenged the prevailing Aristotelian cosmology. He discovered that the Milky Way was not just a diffuse light band, but a massive collection of individual stars, planets, and other celestial objects. The nearest galaxy to the Milky Way is the Andromeda Galaxy, and we think there are about 100 billion galaxies in the visible universe. This means we can actually count the number of stars in the visible universe. Through his observations, Galileo demonstrated that the Milky Way was not at the center of the universe, but instead a vast expanse of stars scattered throughout space. In 1750, English astronomer Thomas Wright proposed a new hypothesis in his work, An Original Theory, or New Hypothesis of the Universe. According to Wright's speculation, the Milky Way was not a random distribution of stars in space, but a completely flat layer of stars. He also suggested that a portion of this vast structure was our own solar system. While Wright's hypothesis was a step forward in understanding the structure of the Milky Way, it was still limited by the observational technology available at that time. People still believed that the Milky Way was all there was to it, and considering the limitations, that's not surprising. However, astronomy made major leaps by the early 1800s, and by the early 1900s, things were changing fast. In the 1920s, American astronomer Edwin Hubble made a transformative discovery using the 100-inch Hooker telescope at Mount Wilson Observatory. Hubble observed distant nebulae beyond the Milky Way. Through the observations and analysis of these objects, he showed that they weren't actually part of the Milky Way, but instead were entirely separate galaxies, each containing billions of stars. One of the closest of these galaxies was the Andromeda Galaxy, also known as M31. This celestial object has a rich history of observations that dates back centuries. One of the earliest known records of this celestial object can be traced back to the 10th century when the Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud in star charts from that period. It was labeled as the Little Cloud, which might have to do with the fact that when you examine it from Earth, it does seem like it has a faint cloud all around it. The significance of these observations lies in the fact that al-Sufi was able to identify this distant cosmic entity without the help of telescopic instruments, relying solely on his keen eyesight and observations. He was able to do that because Andromeda is one of the only galaxies in the universe that you can see from Earth's surface without needing any special instruments. All you really need is to know exactly where to look, and you'll see it right there in the open sky. Sure, you can't go into much detail, but you can still see that something other than the usual stars is there. That's why it wasn't until 1612 that a more detailed description of the Andromeda Galaxy, based on telescopic observations, was provided by Simon Marius. His work ended up laying the foundation for future astronomers to study this massive cosmic structure. Later in 1764, the renowned French astronomer Charles Messier catalogued the Andromeda galaxy as M31 in his well-known Messier catalog, mistakenly attributing its discovery to Simon Marius, unaware of Al-Sufi's earlier work. But that doesn't mean that he didn't have a major hand in putting Andromeda on the map. For almost 100 years after this, astronomers all over the world were trying to understand more and more about this mysterious galaxy, each adding to the last one's findings. A significant leap in understanding the nature of the Andromeda galaxy occurred in 1864, when the English astronomer William Huggins made a groundbreaking observation. He studied the spectrum of Andromeda and noticed that it was different from that of a typical gas nebula. That paved the way for the world to really get to know Andromeda for what it really is. The Andromeda galaxy has a mass estimated to be between 1 and 2 trillion times that of our Sun. It's a colossal cosmic structure that just happens to live relatively close to us in the vastness of space. In all the research conducted until now, scientists believe that Andromeda is about 10 billion years old, making it quite ancient in cosmic terms. Its age hints at a long and intricate history of formation and evolution. One of the intriguing aspects of Andromeda's origin is the hypothesis that it came into being through the merging of several smaller protogalaxies. This suggests that over billions of years, smaller galactic entities gradually came together under the force of gravity to form the majestic Andromeda galaxy we see today. Such galactic mergers are common occurrences in the cosmos, shaping the growth and structure of galaxies. But it all happens so slowly that you can't actually see it happen until major progress has been made. For a long time, astronomers thought Andromeda was significantly more massive than our own Milky Way galaxy. From an objective point of view, a mistake like this could easily be made because we're in our own galaxy, and seeing Andromeda from Earth does make things look so large that you'd easily think there's no way anything could even come close to its size. But that's not the case. Recent research has brought about a reevaluation of these beliefs. New findings have led scientists to somewhat reduce their estimate of Andromeda's mass, while simultaneously increasing the mass attributed to our Milky Way. The Andromeda galaxy's physical dimensions, though, are what astronomers totally agree on. It's known to stretch farther than our own Milky Way, with an impressive diameter of about 220,000 light-years. Andromeda surpasses the Milky Way's estimated diameter of roughly 100,000 to 175,000 light-years. This vast size makes Andromeda a truly significant cosmic entity, taking over a large region in space. This revised perspective also highlights the complexities and challenges of accurately measuring the mass of galaxies. Galaxies are immense systems, and their mass is intricately linked to the distribution and movements of stars, gas, dust, and dark matter within them. Pinpointing these values precisely is a demanding task that requires sophisticated observational techniques and meticulous analysis. So, it couldn't have possibly been done in the 1700s or even in the 1800s. This type of knowledge required modern tools, which is why the reality is just coming to light now. By far, one of the most fascinating features of the Andromeda galaxy is its active galactic nucleus, AGN. The AGN is a highly energetic region at the center of a galaxy, characterized by intense emissions across various wavelengths, from radio waves to X-rays. AGNs are powered by the presence of a supermassive black hole at the heart of the galaxy. These supermassive black holes are incredibly dense regions in space, where an enormous amount of mass is concentrated within a very small volume. When astronomers observe the AGN using advanced telescopes like the Hubble Space Telescope, they notice a very interesting phenomenon. The AGN appears to have 2 points of concentration, meaning there are 2 distinct regions where light and other forms of radiation are emanating more intensely than in the surrounding areas. The brighter concentration is the second point of focus, which is just slightly off the true galactic center. Within this area lies the supermassive black hole. The mass of this black hole has been estimated to be between 1.1 to 2.3 times 10 to the power of 8 solar masses, which means it weighs approximately 110 to 230 million times as much as our Sun. Supermassive black holes are believed to be common in the centers of galaxies, including our own Milky Way, and they play a crucial role in the evolution and dynamics of galaxies. When matter such as gas and stars gets too close to a supermassive black hole, it forms an accretion disk around it. This disk of swirling material heats up and emits intense radiation across various wavelengths, which is why the AGN is highly luminous. When astronomers observe the AGN of the Andromeda Galaxy, they notice a brighter point of concentration near the central supermassive black hole. This feature is a result of the unique gravitational interactions between the black hole and the stars in its vicinity. In the heart of the Andromeda Galaxy, the supermassive black hole exerts an immensely powerful gravitational pull on surrounding stars. As these stars orbit the black hole, they follow elliptical paths similar to planets orbiting the Sun in our solar system. At a certain point in their elliptical orbits, stars come closest to the black hole, and this point is called the perihelion. At the perihelion, gravitational forces are at their strongest, causing the stars to move at their highest speeds. This is when the stars bunch up and become more concentrated in space around the black hole. As they bunch up, the stars release energy in the form of radiation, including visible light and other types of electromagnetic radiation. The increased concentration of stars and the release of radiation create the brighter point of concentration that astronomers observe in the galactic core of Andromeda's AGN. This distinctive feature provides valuable clues about the gravitational dynamics and interactions between the supermassive black hole and the surrounding stars. The Andromeda Galaxy also has an abundance of globular clusters. These globular clusters are tight groups of stars that orbit around the center of the galaxy, kind of like satellites revolving around a planet. Andromeda is estimated to harbor around 460 of these dense and ancient clusters, each containing hundreds of thousands to millions of stars that formed around the same time. The incredible number of globular clusters in Andromeda offers valuable insights into its cosmic history and interactions with smaller galaxies over billions of years. It suggests that Andromeda has been an active devourer of these smaller galactic companions, a process known as galactic cannibalism. As smaller galaxies come within Andromeda's gravitational reach, immense forces strip them of their stars and other components. The stars from these cannibalized galaxies become part of Andromeda's stellar population, adding to the rich diversity of stars present in the galaxy. This characteristic of accumulating globular clusters and stars from smaller galaxies is considered typical for spiral galaxies like Andromeda. Spiral galaxies, characterized by their disc-like shape with distinctive spiral arms, provide an ideal environment for interactions and mergers with smaller companions. In addition to its other intriguing characteristics, recent observations and analysis have sparked speculation among astronomers that the Andromeda Galaxy might be undergoing a fascinating transformation. It appears to be transitioning from being a typical spiral galaxy to a relatively rare type known as a ring galaxy. Ring galaxies are intriguing and relatively rare celestial objects characterized by their circular or elliptical ring-like structures. The rings consist of bright young and blue stars, while the central region contains relatively little luminous matter. These unique features make ring galaxies stand out among the vast array of galactic structures. In the realm of normal galaxy morphology, there are three main types of observed optical ring phenomena: nuclear rings, inner rings, and outer rings. Nuclear rings are located near the center of a galaxy, while inner and outer rings are a bit further out. But it doesn't end here. There are two primary types of ring galaxies: O-type and P-type. O-type ring galaxies have centrally located nuclei, and their rings are smooth and regular in shape. On the other hand, P-type ring galaxies have off-center nuclei, and their rings tend to be more irregular. Ring galaxies are considered rare cosmic gems, with only approximately 1 in 10,000 galaxies classified as them. Astronomers have actually proposed two main mechanisms for the formation of ring galaxies. First, they can form through the collision of two or more galaxies. Second, a smaller galaxy passing through the center of a larger galaxy can also trigger the formation of a ring-like structure. Examples of ring galaxies thought to be formed through galactic collisions include the Cartwheel Galaxy, Galaxy Pair 2026-424, and RP-147. So, it's not just a simple galaxy. There are lots of intricacies at play. But what's happening right now is even more interesting. Scientists say that the Milky Way galaxy and the Andromeda galaxy are on a collision course and will eventually merge to form a new supergalaxy. This colossal event has already gotten nicknames like Milkomeda or Milkdromeda, since it's known all over the world now. Even though these nicknames are pretty playful and fun, the consequences of this merger for humanity would be devastating. As the two galaxies approach each other, their immense gravitational forces will cause them to distort each other's shapes. This interaction leads to tidal interactions where stars, gas, and dust are pulled between the galaxies. The galaxies will begin to overlap, causing mayhem and destruction everywhere. But it won't happen all at once. As the galaxies continue to draw closer, their collision initiates the merging process. Stars, gas clouds, and dust clouds from both galaxies interact and mix together. This process can lead to the formation of new star clusters and structures within the newly merged galaxy. During the merger, stars experience significant changes in their orbits, leading to a dynamic and chaotic environment within the merged galaxy. Some stars might even be flung out of the new galaxy, while others settle into new, more elliptical orbits. Both galaxies harbor supermassive black holes at their centers. During the collision, these black holes will eventually merge as well, forming an even larger black hole at the heart of the newly combined galaxy. The merging process can trigger bursts of star formation in regions where gas clouds collide and compress, creating new stellar nurseries. These nurseries become the birthplaces of young, massive stars fit for the new galaxy. As the galaxies merge, the night sky becomes a cosmic light show. The collision and subsequent merging will also create stunning displays of star clusters, shock waves, and bright bursts of radiation. The night sky transforms as new constellations and stellar arrangements emerge. In simple terms, the entire sky will change and become brand new. But the thing is, while these things will be happening on a grand scale, the effects run deep. As the Andromeda Galaxy and the Milky Way merge, the immense cosmic forces and interactions between stars, gas, and dust will trigger significant changes in the environment on Earth. These alterations can have varying effects on the biosphere, the regions of the Earth where life exists, potentially leading to disruptions in habitats, shifts in biodiversity, and causing local extinctions. The merging of galaxies could lead to disturbances in the solar system, impacting Earth's climate and weather patterns. Changes in temperature, precipitation, and weather events might start happening all over the world, influencing the distribution of vegetation and animal habitats. The shift in solar radiation might affect essential processes for plant and animal life, potentially causing disruptions in ecosystems, so their lives might be at stake. That too, a lot earlier on in the merging process. Plus, an increase in cosmic radiation within the intergalactic region could impact Earth's atmosphere, including the ozone layer. These changes could, in turn, affect climate patterns and have implications for the survival of various species. The altered atmospheric composition might influence photosynthesis, and other essential processes that sustain life on our planet. As climate and ecosystems transform, existing habitats for various species could become less hospitable or shift entirely. Many animal species rely on specific migration patterns for breeding, foraging, and survival. The disruptions in habitats and changing climate might interfere with these migration routes and timings, leading to challenges in finding food, water, and suitable breeding sites. With the shifting climate and habitats, biodiversity, and the variety of life forms within an ecosystem could also experience changes. Some species may thrive in the new conditions, while others may struggle to survive. Increased competition for resources could occur, and new opportunities might emerge for certain species to flourish in the altered ecosystems. Unfortunately, there will also be animal species that may be unable to adapt quickly enough to the new conditions, leading to local extinctions. Disruptions in habitats and migration patterns can have cascading effects on the entire ecosystem, potentially resulting in the loss of certain species from specific regions or habitats. While all of this is heartbreaking, the reality is that even if the galaxies are on a collision course, the process won't actually happen overnight. The collision is expected to begin approximately 4 billion years from now, and the entire merging process will take another 2 billion years to complete. As for our species, we will be long gone by then, and our planet Earth will have undergone tremendous changes long before the collision even begins. Around 5 billion years from now, our Sun is projected to evolve into a red giant, eventually expanding and engulfing the inner planets, including Earth. This process will likely render our solar system uninhabitable long before the merger between the two galaxies takes place. If some descendants of our species or other life forms exist around 4 to 6 billion years from now, they will be incredibly distant from us in evolutionary history, nothing like humans today.